Alright, this video is going to go over the aspirin synthesis and analysis lab. In part 1, you measured the mass of salicylic acid you used. You also should have measured the volume of acetic anhydride you used, and you should be able to use the density of the acetic anhydride given in the third row along with the mass to determine, along with the volume to determine the mass of acetic anhydride that you used, and then you measure the mass of aspirin synthesized. So the only calculation you have to do in that first data table is with the mass of acetic anhydride. In part 2, you measure the melting point of your sample twice, and then the average is just a calculation. You do need to complete your data tables, but unless I explicitly ask for the calculation to be shown in the questions, I don't need to see it separately. Part 3 is the part that we did for the most part on Monday, and that's the part I want to make sure I talk a little bit more about, make sure that that's clear, because I think the first parts are. So the stock solution was one I made, so you do not have that information. I have put for you, or typed in for you, the amounts I used, the moles I used, and the molarity of the solution that I made. And then remember with the dilutions that I took 10 mils of I think you took 5 and I took 10 mils of my stock solution, and I added it to the copper nitrate and to a 100 ml volumetric flask. And when I did the absorbance readings for dilutions of the standard solution, those were the data points I got, and I gave those to you in lab if you were not in lab during the time I posted those, or if you were not in class that day. You need to make sure you get those, because it is that set of data, the Beer's Law data, that you will need to graph. You can use your calculators to make a list, have L1 be your x-axis list, which would be concentration, L2 be your y-axis list, which would be absorbance, and then you can do a calculation under statistics that will allow you to do a linear regression, and it will give you the best fit line for that data. That's what you need to put in this box here. Okay, so it'll be in the form of y equals mx plus b, y being your absorbance, m being the slope of the data making up these points, and then x being your concentration. So make sure you record those. Again, best fit line is the b is going to hopefully be close to 0, but just to remind you from before when we covered Beer's Law, trying to see if I can find the graph that'll look like it. Basically, we're taking different concentrations, and as the concentrations increase, so does the absorbance. Sorry, that's not all completely in your window. And that's still not any better. Oh, hold on one second, I'll get it better for you. We'll visit the page, see if that makes it any easier. Okay, and so the 4 standards I used to prepare the graph for you, and then you are going to take the absorbance reading you got for your unknown solution and use that regression line to determine its concentration. Okay, so I don't think I need any help with tutoring, so I'm going to close this out for us. So once you get that, you'll move on to the chart on the back. It is here where you should have put the amount of aspirin that you measured out to make your sample that was tested, along with the absorbance reading of that sample. And as I just talked about, the best fit line that I generated for you at the standard solutions, you'll use that to determine the concentration of your aspirin sample. Remember that that reacted with the salicylic acid that was remaining from your aspirin sample, and that you can find the moles of the salicylic acid that were present that were unreacted by taking that molarity and combining it with the volume, and you made 100 mils of that solution that you tested. Once you have the moles of that, you should be able to convert to grams using molar mass, and then you're going to figure out how much aspirin was actually in your sample compared to the salicylic acid. There are only 2 reactants. One evaporated, but we had 2 that could possibly leave a mass, and that would be the aspirin and what you made, and then the salicylic acid, which was not completely consumed. So together they make up the mass of your aspirin sample. So if you know the mass of the salicylic acid from this row, you should be able to use the mass of the aspirin sample that you measured back in part 1 to figure out how much aspirin was actually present in your sample. And based on your melting points, it seems like some of you got some pretty good results with that. Others of you might not find that you had as much aspirin present as you thought. So to calculate the percent of aspirin, you take the grams of aspirin that we just got up here, and we divide it by the grams present initially from our part 1 of our lab, and multiply by 100. And I'll be honest, the more I look at aspirin, the more I'm starting to think I misspelled it, but I'm sure it's probably okay, but I apologize if I did do that. Alright, so that'll help you fill in your data tables. Now we're going to talk about the 6 questions. First one says, what is the theoretical yield of aspirin? And that the ratio between salicylic acid and acetic anhydride was 1:1. You had 2 reactants, so you need to figure out which one was limiting by looking at their moles. The one with the fewest moles is your limiting reactant, and then take that limiting reactant and figure out, stoichiometrically wise, how many grams of aspirin could be formed. Next, you're asked to do a melting point, or look at your melting temperatures to look at the percent purity of your sample. You're going to evaluate that by taking the melting point of your tested aspirin, the average value, dividing it by the theoretical one, which was given to you up here in number 2. And I think one group did not get their sample to melt before 150, so for you all, I want you to use 151 as your experimental value. You're going to do the same thing in number 3 with percent purity, but you're going to basically use percent purity as the percent aspirin that you showed up here in your chart. So I would like to see the calculations for number 1, for number 2, for number 3, as well as for number 4. So how you calculated the percent aspirin, which you filled in your table, the very last row in your table, that calculation I want to see for number 3, but the rest you can just write your values. You don't have to show work for those calculations unless you wish to. Number 4 says use your percent purity to determine the percent yield of your synthesis of aspirin. Percent yield is actual over theoretical times 100. We've seen that already this year. Theoretical is what you determined in number 1, and your actual yield will be taking the mass of aspirin you made from part 1 of the lab and multiplying it by the purity. Because the purity is a percentage, we do need to divide that value by 100 to get an amount that's more feasible for your actual yield. So that should help you with number 4. Again, show me that calculation. For number 5, you can Google the 4 compounds, or the 4 components of this reaction, and come up with their structures. The structures I'm talking about are like what you drew when we were doing Lewis structures in class. And so I want you to use those to represent the 4 components of your reaction. And then I want you to identify functional groups. We did that when we covered organic. So if you go back to your organic notes, and this was included, I know we didn't quite finish that whole thing out, but I know that this part was in your notes for that. So if you go to the organic notes that I gave you in class, these are the different functional groups. So you're looking for different ways that atoms can be connected in an organic compound, because these functional groups tend to have characteristics that make them unique for that particular type. And you can have multiple functional groups within one organic compound. So I want you to see what you can find present in your organic compounds that represents these different functional groups. And that is it for the lab. Because I will not be here to be able to answer questions for you, you may have until Tuesday at the beginning of class to turn in your lab. So that would be March 1st. And if you need help on it, you need to come in before class on March 1st. Okay?